You're moving along a road, and this road has parts that are windy, parts that are straighter, and you'd like to know, is there a numerical value that you can describe the curve by? We call curvature this number as we move through space in a space curve, and I want you to think about circles. If I drew a tangent circle at this point, a tangent circle at this point, a real tiny one at this point, the greater the curvature, the smaller the circle. The straighter the road, the bigger the circle. So first of all, we recognize there's probably an inverse relationship between the size of the circle and the curvature. The next thing I want you to notice is the unit normal vector and the unit tangent vector. The unit normal points in the direction of the center of the circle in every case. Now, we mentioned before that all motion is either straight, circular, or some combination. So as I'm moving down the road, the unit tangent is my straight portion. The unit normal is the part that dictates the circle. So now let's look and see if we make sense of this. So if I have a curve and I said, consider every unit of arc length, and I draw the tangent vector for each one unit, then essentially the rate of change of the direction of the unit tangents per unit change in the arc length would be a good way to describe curvature, because if I had a very tight road here, you'd notice that the tangents are changing very rapidly. So from this we come up with the definition of curvature. We use capital K. Think of the change in the direction of the unit tangent per unit change in arc length, and we want that magnitude. Now that's kind of a strange quantity because we don't usually use S as our variable here, we usually use T. So if we use the chain rule at this point, and we notice that since S is a function of T, then dt dt must be dt ds times ds dt, this being a vector, this being a scalar quantity. We know this is the arc length parameter, so it is non-negative. Now, since we want to find ds dt, or dt ds, we simply multiply both sides by the reciprocal. Now, this is not a trivial quantity to compute as we've seen before, but we know how to find it. We also know how to find this guy. So if I said then curvature, which is the magnitude of dt ds, is therefore this quantity here times this magnitude. Now, hopefully you've noticed this guy right here we've also shown is the magnitude of the velocity vector. So very conveniently we can also write this as dt dt's magnitude over the magnitude of the velocity vector. Now, I've posted extensive notes on curvature in the notes section so you can follow through. Basically, coming up with this quantity is not really that difficult in general depending on the curve.